Our first project is based on a dataset freely available and prepared by Angelo Oliveira. The dataset contains portable executable header information with many features and also labeled if malware available or not. Let us first understand what portable executables and finally portable executable headers are. Portable executables are data structures which are required by the operating system to handle executable code. The PE format was designed to do the following steps. First, the PE format describes where and which parts of a file should be loaded into memory. It describes where in the code the operating system should start executing the program. Then, the PE format allocates resources of a running program which can be used for its execution. These resources can be of any type like images, videos or graphical user interfaces dialogues. Finally, the PE format provides digital code signatures which the operating system uses to allocate a trusted source which the code comes from. A PE format has a series of headers, which communicates to the operating system how to load the program code into its memory. One of these headers is the PE header, which the operating system uses to load the program content from a file into the memory. The PE header has also the address, where the execution of the program starts, and a list of functions on which the program code relies on. The PE header has the necessary information for helping the OS to load and execute the program code properly. The provided datasets have PE headers which will be explored in detail later.
The dataset which we want to build a robust binary machine learning model can be downloaded within this course as CSV and as attached. Let us get started within Google Colab to create our machine learning model for binary malware classification. First, as in all machine learning applications, let us create our necessary environment by downloading basic libraries in order to kick off creating our binary classification model. We install scikit, and imbalanced-learn libraries. Imbalanced-learn library is required for creating synthetic data, which will be explained later. Then, we import NumPy, pandas, and for data visualization matplotlib and cbin. For Scikit-learn, we import all necessary machine learning algorithms and metrics for model evaluation. The CSV files, which includes the necessary datasets, will be uploaded to the Google Drive, and finally mounted within Google Colab on a defined path for further usage. We create one single database, DF, out of both CSV files and drop duplicates. Let us see what features our new created database has. The dataset consists of 1007 columns. Columns with continuous values are our hash label, size of data, virtual address, entropy, virtual size, and malware X and Y. All other 1000 columns have categorical values. The classification column is malware, and 1 means malware is non-existent and 0 means malware does exist. Now, let us check and visualize how class distribution is given among columns malware X and Y. These columns were each in one of the provided original datasets. We will again cross-check class distribution in 1 minute. Here let us see what a heat map can indicate and if correlations exist among picture and class columns of the first 6 already mentioned columns. Now we would like to understand which column values do have a significant correlation and therefore need to be considered. Correlation is between -1 and 1, in case correlation is near plus and -1 and significantly above plus and -0.1. We can assume high correlation between 2 parameters. Outlined in red and high correlation value, we see correlation between the feature's virtual size and size of data. Let us check how many in our dataset. Okay, it is 0. And now we want to drop one malware column and rename the other malware column for further processing. Let us move on to count binary classification values of malware values, and finally visualize it. As expected, we see an imbalanced distribution of non-existent malware and malware. Now, we need to change the data types of our modified dataset in order to process them for further analysis. Before continuing our journey, Let us get our intuition for cross-validation techniques and decide which one to use within this project. Machine learning models must be robust in order to work accurately for real data, which has never been seen before. The model must be low on bias and variance. This process of deciding, rather than numerical results quantifying hypothesized relationships between variables, are acceptable as descriptions of the data, is known as validation. One step further is that your robust machine learning model is able to generalize to an independent or unseen data set, and this fundamental step is known as cross-validation. We would like to describe here some widely known cross-validation methods and finally apply one for building a robust machine learning model. In order to pick the correct cross-validation method, we need to have a good understanding of our data. An iterative process is essential, in case the chosen machine learning model is applied on unseen data, and finally make optimizations or change the machine learning model to get a robust result considering our chosen cross-validation method. First, let us start to get an understanding of the definition of stratification. Training a machine learning model with a highly imbalanced dataset can be misleading and end up in incorrect misclassification and prediction according to our known evaluation metrics. The iterative process of fine-tuning a machine learning model includes not only using different machine learning algorithms and hyperparameter optimization. It must be considered that an appropriate preparation of training data for building a robust machine learning model does have a significant impact on the robustness of the model. For binary classification problems with highly imbalanced training data, it must be considered that class distribution of training and test datasets is critical before selecting and tuning different machine learning algorithms. Randomly splitting data for training and testing the data is not sufficient, as proportions and distributions of majority and minority clause need to be ensured to avoid results like, for example, overfitting. Different approaches to prepare a dataset for train and test can be used, but for imbalanced datasets split randomly in a way that ensures same class distribution in each subset through stratified sampling. The class is used to control the sampling process. Finally, special attention is required also for resampling procedures like cross-validation on a limited data sample to ensure distribution on all input variables X in order to calibrate a machine learning model. Now, we have a quite good understanding what stratification means. Let us move on to understand stratification and train-test split. The machine learning framework, scikit-learn, can split your dataset ensuring stratification by defining classes or target variable, and assigning it to stratify parameter within train-test split. It is possible to customize train and test size as required, and generally between 60 and 80% of the dataset is chosen for training data. Another parameter which is set by default 25% for proportion of test data is the test parameter, which can be also customized. It is recommended to use the stratify parameter setting any time for a classification task and imbalanced dataset. This can be done by setting the stratify argument on the call to train test split and setting it to the y variable, which contains the target variable from the dataset. From this, the defined Python function will determine the desired class distribution and ensure that the train and test sets both have this distribution. And now, let us move on to understand GITHUB. A resampling method through cross-validation to evaluate the machine learning model performance on limited data sampling is known as GITHUB. A defined subset that a data set needs to be split into is referred as K. The letter K is often used to represent a constant value, for example for K nearest neighbors, which K refers to number of neighbors. In case the training dataset is randomly splitted into folds and stratify classes to ensure a suitable distribution among training data subsets, the trained machine learning model is biased when test data is used to evaluate the model. GITHUB cross-validation take one group of the created K groups as holdout set to evaluate the model. This step is done K times to ensure that all groups have been represented once in the holdout set. There exist many variations of the cross-validation method GITHUB, and here we would like to introduce you to one widely used variation, which is known as stratified GITHUB. You can understand stratified GITHUB as a method to shuffle data and split it into different proportions with proportional class distribution among splits. In case the parameter shuffle is set to true, the data will be finally shuffled by the random state. Finally, you have similar splits for each fold with the same amount of data from each class. In case you define and splits equal to 4 and have two classes for target label y, 4 training sets cover all test and train data without any overlap. Each of the examples in the minority class will be used in a test set, and each train and test data set for each split has the same class distribution. This example highlights the need to first select a value of k for k-fold cross-validation to ensure that there are a sufficient number of examples in the train and test sets to fit and evaluate a model. It also highlights the requirement to use stratified k-fold cross-validation with imbalanced datasets to preserve the class distribution in the train and test datasets. Another cross-validation variation is stratified shuffle split, where the data is shuffled and then split into predefined n splits. One split is taken to be used as test set. This process repeats other times as per predefined iteration. With this method, an overlap of test data among folds cannot be avoided. The main difference between stratified shuffle split and stratified k-fold is that stratified k-fold just shuffles and splits once. Finally, therefore, the test sets do not overlap, while stratified shuffle split shuffles each time before splitting and splits times so the test sets can overlap. Cross-validation and stratification are key in order to train and test a robust model for classification. The method stratified, shuffle, split results in overlapping test sets, which can mislead in fluke results. This method will not be used for creating machine learning models with our dataset.
Thank you, Grace, for some insight into cross-validation methods. Now, we want to apply in our project the already mentioned and widely used stratified k-fold method, where the whole evaluation process of stratified k-fold is repeated according to parameter settings n repeats and 5 splits. With this method, fluke results can be avoided and variance of the model can be better captured. Let us check the shapes of training and test data. We have found a suitable solution in order to train and test our model by applying a widely known cross-validation method, stratified k-fold. And now, we would like to generate synthetic data of the minority class in order to apply different machine learning models to create a robust binary classifier. Now let us check the dimension of the new created synthetic trained data and compare it to the newly created label trained data. Okay, that looks good. We import a counter to understand class distribution among the newly created synthetic data. And here we go. Class distribution looks pretty good and can be processed with other machine learning algorithms. Generate synthetic samples. Machine learning models will have poor performance in case of labeled data from minority class for highly imbalanced data. For highly imbalanced data scenarios, over and undersampling techniques can be used with the aim to have more balanced training data and build a robust machine learning model. In case of undersampling the majority class, we can expect that useful information having impact on building our binary classification machine learning model can be lost. So in our example we will focus on oversampling techniques. A very common and widely used approach synthesizing new data examples is called synthetic minority oversampling technique or SMOTE, which creates artificial samples of the minority class through interpolation. This oversampling method does not rely on replacements, it is based on feature similarities between existing minority examples. This approach can balance finally the class distribution but does not provide any additional information to the model. SMOTE has various variances for different data types. The main package behind SMOTE is imbalanced-learning. With our dataset we will use SMOTE with mixed continuous and categorical values, which is an extension of SMOTE to SMOTE-NC. SMOTE-NC is synthetic minority oversampling technique for nominal and continuous. With this unique library, the most common occurring category of nearest neighbors to a minority class point is taken. First, we define categorical features and resample the minority labeled class. And finally check the balanced distributed labeled synthetic data. Our first machine learning model is decision tree. A decision tree can be used for classification and regression problems. A training model based on the available training data is created in order to predict if malware is available or not by learning decision rules. A decision tree is started from root of the tree. An iterative comparison process is started by comparing the root attribute with the records attribute. Based on the result of the comparison, The optimal identified branch which match up with the root value is followed, and finally the next node in the decision tree is followed. In other words, decision trees classify examples by sorting them down the tree from root to leaf nodes. Finally, the leaf provides the classification of the example. Within each node in a decision, a test case for attributes is generated, and each edge which descend from a node correlates to possible answers to the test case. This iterative process is repeated for every subtree next below to the node. So, the question here is, how does a decision tree work? The main drivers behind a decision tree are algorithms and attribute selection process. Multiple algorithms are used for decision to split a node into two or more sub-nodes and is based on target variable type. A decision tree splits nodes on all available variables, and finally chooses the suitable split which results in most equal sub-node. On the other hand, attribute selection is crucial for building decision trees. Criterions like Gini index and ratio, information gain and entropy calculate values for every attribute. Finally, values are sorted and the corresponding attributes are prioritized. In case an attribute has a high value, it will be placed at the root of the tree. Finding an attribute with highest information gain is one of the main goals when creating a decision tree. Now, let us create our decision tree classifier with our training data and make predictions with the created binary classifier and our test data. As already mentioned are the required steps to visualize our decision tree. Classifier and we calculate. Alright, now let us calculate the F1 score. Next, the precision score, the recall score, the accuracy score, the balanced accuracy score, the Matthew correlation coefficient, and finally our most important metric for highly imbalanced data, the average precision score. Now, we want to plot the average precision score to understand better the average precision curve. The result of average precision score is 0.87. And now, let us move on to the confusion matrix. At least in 11 cases, malware has been incorrectly misclassified. Now, we calculate the receiver operating characteristic and plot the ROC curve. T. His step is just for information purposes and the value out of this step is limited. Finally, we would like to plot training and testing learning curves to understand how accuracy is behaved. Alright, now we take on the next machine learning model, random forest classifier. Random forest is an ensemble learning algorithm, thus it is a combination of machine learning algorithms. The main differences between random forest and decision tree is that the training data set is randomly sampled when creating trees and subsets of features are considered randomly when splitting decision tree nodes. The training data samples are made with replacements, also called bootstrapping. This means that some samples will be used several times in a singed tree. The purpose is that by training each tree on different samples, each tree might have high variance regarding to a subset of the training data, but the entire forest will have lower variance without increasing the bias. During testing the random forest classifier, predictions are based on averaging predictions of each tree. This process is called bootstrap aggregating, which means that each unique learner on various bootstrapped subsets of data is trained and finally predictions averaged, which is known as bagging, short for bootstrap aggregating. Another concept behind random forest is that only a subset of all features are considered when splitting each node in every decision tree. For example, if there are 16 features at every node in each tree, only 4 random features will be taken for splitting the node. Let us summarize in other words how to differentiate a random forest with a decision tree. A random forest combines in some cases even thousands of decision trees and trains each tree with different set of observations and split nodes in each tree considering only a subset of all features. Finally, by averaging the predictions of each tree, final predictions are generated by the random forest. Now, let us create a random forest classifier with our training data and make predictions with the created binary classifier and our test data. Now let us calculate the F1 score. Next, the precision score, the recall score, the accuracy score, the balanced accuracy score, the Matthew correlation coefficient, and finally our most important metric for highly imbalanced data, the average precision score. Now, we want to plot the average precision score to understand better the average precision curve. The result of average precision score is 0.92. Let us move on to the confusion matrix. At least in 15 cases, malware has been incorrectly misclassified. Another ensemble technique and widely used machine learning algorithm called XGBoost will be applied to create a binary classification model. So, the question is, what is boosting doing? Boosting implement a sequential process, where each model tries to correct errors made by the previous model. The main purpose is to optimize the performance of the learners. In other words, gradient boosting employs the gradient descent algorithm to minimize errors in sequential models. Boosting can be described as developing a more dynamic evaluation process and with gradient descent errors are corrected. A big disadvantage is that gradient boosting creates only one decision tree at a time. XGBoosting features parallel tree building, regularization and cache-aware access. It is highly customizable, sequential where you can tune hyperparameters. Let us summarize what we have learned so far about tree-based models. A decision tree can be described as a graphical representation of possible solution to a decision based on conditions. Random forest is a bagging-based algorithm in which only a subset of features are selected randomly to finally build a forest of many decision trees. XGBoost is an optimized gradient boosting algorithm with tree pruning and regularization to avoid overfitting and bias. Now, let us create a XGBoost with our training data and make predictions with the created binary classifier and our test data. Now let us calculate the F1 score. Next, the precision score, the recall score, the accuracy score, the balanced accuracy score, the Matthew correlation coefficient, and finally our most important metric for highly imbalanced data, the average precision score. Now, we want to plot the average precision score to understand better the average precision curve. The result of average precision score is 0.86. And now, let us move on to the confusion matrix. At least in 14 cases, malware has been incorrectly misclassified. Now, we calculate the receiver operating characteristic and plot the ROC. Finally, we would like to plot training and testing learning curves to understand how accuracy is. A relative newcomer in the field of gradient boosting algorithms is Catboost. This algorithm differs from other gradient boosting algorithms by two main items. First, other gradient boosting algorithms are affected by subtle types of data loss due to overfitting process they undergo. Catboost addresses this by an artificial timeline to ensure that the chain of training examples is continuous and without leakage. Another feature which differentiates the Catboost algorithm from other gradient boosting algorithm is that at each level of the tree, same features and criterion is used, so therefore many examples can be processed parallel, which finally makes Catboost fast. With this approach, a tree ensemble is created, which is a group of weak learners is created, and therefore errors and bias can be minimized. We need to download Catboost libraries before creating our model. Let us calculate the Catboost F1 score. Next, the precision score, the recall score, the accuracy score, the balanced accuracy score, the Matthew correlation coefficient. As in previous models, our most important metric for highly imbalanced data, the average precision score. Now, we want to plot the average precision score to understand better the average precision curve. Finally, let us give an introduction on k-nearest neighbors. Comparing to other machine learning models, k-nearest neighbors is relatively simple. This algorithm works on measuring the distance between data points and makes pattern to create a certain relationship between 2 points. Based on the results, it decides in which neighbors new data samples should be placed. The label of the new samples will be defined from these neighbors. K-nearest neighbors is widely used with the standard Euclidean distance of measuring the distance between 2 points. The constant value k is for the number of nearest neighbors, which have a minimum distance from the new created data values. So, let us calculate the k nearest neighbors F1 score. Next, the precision score, the recall score, the accuracy score, the balanced accuracy score, the Matthew correlation coefficient. As in previous models, our most important metric for highly imbalanced data, the average precision score. Now, we want to plot the average precision score to understand better the average precision curve. The result of average precision score is 0.67. And now, let us move on to the confusion matrix. At least in 33 cases, malware has been incorrectly misclassified. Let us move to the next, perhaps most widely used algorithm for binary classification, logistic regression. Similar to linear regression, logistic regression make estimations on the parameters used in the prediction equation based on the training data. Logistic regression predicts the probability of an class that is dichotomous dependent on other factors and is categorical. Output of a logistic regression is between 0 and 1 and very suitable for binary classification tasks. The core function behind logistic regression is the S-shaped sigmoid function, which takes any data value and map it into a value between 0 and 1. In case the curve goes to positive extend and is more than 0.5, the target class will classify it as 1, and if the curve goes to negative extend and less than 0.5, the target class will be classified as 0. So, let us calculate the logistic regression F1 score. Next, the precision score, the recall score, the accuracy score, the balanced accuracy score, the Matthew correlation coefficient. As in previous models, our most important metric for highly imbalanced data, the average precision score. Now, we want to plot the average precision score to understand better the average precision curve. The result of average precision score is 0.14. And now, let us move on to the confusion matrix. At least in 37 cases, malware has been incorrectly misclassified. Now, we move on to another widely used machine learning algorithm, the Gaussian naive Bayes. A Gaussian naive Bayes classifier is based on the Bayes theorem. We have two events A and B. By using Bayes' theorem, we find the probability of A happening under the condition that B occurred. So here the observed event B is the evidence and A the hypothesis. Main assumption is that predictors and features are independent. This is the reason why it is called naive. In case predictors have continuous value and are not discrete, the assumption is that the values does have a standard deviation like a Gaussian distribution. So, let us calculate the naive Bayes classifier F1 score. Next, the precision score, the recall score, the accuracy score, the balanced accuracy score, the Matthew correlation coefficient. As in previous models, our most important metric for highly imbalanced data, the average precision score. Here, we stop with further analysis as the naive Bayes classifier is absolutely not suitable to be considered due to the model metrics.
In order to choose a robust binary classification model, we take a low number of false negatives and high average precision as well as balanced accuracy metric into account. In our model comparison summary, it is clearly outlined that tree-based models as well as the Catboost algorithm have a robust and good performance to detect malware. We hope that you have enjoyed this lesson and you have the opportunity to implement machine learning algorithms to detect malware. Thank you for watching.